Good afternoon. Is this working? No? Yes? What? Is it working? Yes. Okay. Thank you, George. Welcome to MCube's weekly seminar series. I'd like to remind people that if you have questions during the actual seminar, I'm sure there'll be lots for Chris. Please sort of wait for the microphone so it can be recorded so everybody at home can hear as well. Also, want to remind everybody that Chris will be out in the hallway after the seminar, hopefully, for socializing. We have lots of good cookies and drink and so forth. So the discussion can continue on. So as you probably gathered, today's speaker is Chris Davis. Most of us have known him for quite a long time. He has a PhD in meteorology from MIT from 1990. Was an NCAR ASP postdoc from 90 to 92. And he's now a senior scientist in MCube. He's had many leadership roles in NCAR, from MCube division head, ASP director, NCAR senior advisor. In 2020, he chaired the World Weather Research Program Science Steering Committee within WMO. He's a fellow of the AMS, twice awarded the UCAR Publication Prize, twice awarded the UCAR Technology Prize, once the UCAR Mentoring, and gave the Simons Memorial Lecture in 2007, and he also received the Joanne Simpson Mentorship Award in 2018. Chris's work has concentrated on mesoscale and synodic-scale phenomena such as extratropical cyclones, tropical cyclones, mesoscale convective systems, and terrain-induced flows. He is active in field research, big programs such as BMX and Predict, modeling and theory, giving the complete view of everything. This is all fine and good, but what I really know Chris for, having known him for 30 years at least, 33 years, what I remember most is a piece of burnt toast, which forced us one afternoon to socialize out in the parking lot for about 45 minutes. What that has to do with today's seminar, I have no idea, but Chris, it's all yours.
Thank you, Morris. That was actually a bagel, not a piece of toast. And yes, the fire department did come. Some of you may remember this, and I will never be allowed to forget it. Okay. Anyway, on to the topic of this particular presentation, which is about, obviously, hurricanes and about the intensity problem in hurricanes. It's not going to be so much about prediction of rapid intensity change or topics like that. It's really going to be about how models, and especially global models, resolve or depict the intensity of hurricanes, and maybe what we can learn from some actually fairly simple diagnostic techniques about that. So just a little bit of motivation. First of all, I want to thank, I'm deeply indebted to my collaborators, Rosamar and John Martinez. Rosamar actually created a lot of the framework in the second part of this talk that I'm going to be using, and so it's the Aquaplanet simulation is a very valuable tool. So without that work, this talk would not be possible. So anyway, I'm going to focus on, well, thinking about this as a global modeling problem for the most part. A lot of our prediction of tropical cyclones depends on global models. Yes, regional models are used. They're used quite well. But as global models are forging ahead, they're getting now down below 10-kilometer grid spacing. We're able to depict tropical cyclones very well. And I think there's still a lot of questions about that, but at least in principle, it allows us to get down to the scale where we're resolving the inner core, and I'll show you that in a minute. But there's still a lot of uses for global models where the tropical cyclone remains marginally resolved, and that is for climate projections, large ensembles, seasonal prediction, where we want to know a lot about the intensity, and we're not really able to resolve it And so what can we learn and what are the limitations? So that leads to the two questions here of what are these models capable of resolving? And as we look across the different applications with these models, they invariably change the mesh spacing, the grid spacing, and we get different results for intensity. Is there any way we can say whether those results are self-consistent at all? And what do we even mean by consistency? I'll try to define that in the rest of this talk. So I realize not everybody is an expert in tropical cyclones, or I assume you all have at least some exposure to the topic, but I think the figure on the left from Rogers 2012 is a good place to start in terms of just summarizing the structure. And this is the normalized radial coordinate. So we find out in radius where the maximum wind occurs, and we give that a unit of 1 and normalize everything according to that. And Rob Rogers et al. Composited a lot of observed storms based on hurricane reconnaissance for the most part, and came up with this composite. And you can see that by definition, the maximum wind speeds in this composite of hurricanes are sitting at r equals 1. And that the wind falls off as you go further out. More to the point, though, that area near r equals 1 in this plot is where a lot of the attendant hazards are, or just outside that region. So the extreme wind, the extreme precipitation, and the storm surge are kind of, they're not all right there, but they're often fairly close. And so it's this inner core region that we really want to resolve, and we really want to represent well if we're trying to understand and predict the total hazard that a hurricane represents. Now, if you look on the right, what I've done here is a calculation, and this is based on results that came out in a paper I wrote a few years ago. What we're looking at is what is the distribution of that parameter, the radius of maximum wind. And this is for the Atlantic, and so that's the distribution of radius of maximum wind in kilometers. And you can see that the mode of the distribution is between 15 and 30 kilometers. So that says that the typical radius of maximum wind is in that range. It's a very skewed distribution. You get a few very small storms. And again, this is lifetime maximum intensity. So this is when the storm gets to its strongest, what does this distribution look like? I'm going to be talking about lifetime maximum intensity throughout this presentation. You can see the median of that whole distribution is just over 30. So when we start talking about models whose horizontal grid spacing is comparable or greater to that, then we obviously are going to have an under-resolved situation. And that's what I'm really going to be focusing on. A little bit more on what this distribution of radius of maximum wind actually looks like. And again, this is from observations. And so each point is one storm in the Atlantic database from the years on the previous slide, 88 to 2014. And you can see that there's sort of two regimes in this diagram. On the left side, which is for the weaker and to marginal medium intensity storms, the radius of maximum wind can kind of take on any value. And that's because these storms are relatively disorganized. When they get to their maximum intensity, it's not that great, and they've never really, in a sense, gotten their act together to have a coherent, organized structure. They're often extremely asymmetric as well. But when you move toward the right of this diagram, you see that the radius of maximum wind distribution settles down. They're all less than about 60 kilometers. Many are less than 30, and as you get to really intense storms, some of these get even smaller. So the point of this figure is just to say we're going to be tending to focus on the right half of this diagram in this particular talk. So major hurricanes, and that's category 3 and greater. Those for the vertical bars are roughly the wind speed where those categories on the Saffir-Simpson scale come into play. So category 3, 4, and 5 are major hurricanes. So I'll be talking about that, and also just categories 4 and 5 as well. So here are a couple of examples of global models, and these are not recent examples. They come from a while ago, just to give you a sense for how many, the number of intense storms that are occurring in these models. And one is based on CAM on the left, and the other is based on the high floor model from GFDL on the right. Let me just focus on the right for a minute. It's a complicated picture. The things to look at are, it's an ensemble of several members for seasonal prediction. And when you look at the green line, that is the number of category 4 and 5 hurricanes per year. This is for the North Atlantic. And in black is the number of observed Category 4 and 5 hurricanes during the same time period. You can ignore the dots, you could ignore the shading. What you see is that on average, I mean, this is a really good result. It's a really interesting result. This model at a 1/4 degree grid spacing is able to simulate most of the Category 4 and 5 hurricanes in the Atlantic. So, but the question I'm going to raise is that what it should be doing? Is that what we expect it to be doing? And if not, what is the result we expect? And what are maybe the consequences of this? I just want to say, though, that this is it's a really significant and impressive result overall to get the seasonal behavior here right. So clearly doing something right in this model. Okay, now this is based on a paper that came out 5 years ago, so now it's getting a bit long in the tooth, but I'll talk about this as kind of a motivating for the rest of the talk. So in this part of the talk, and I encourage you to go to this paper, we're doing something that seems at first glance maybe kind of silly. We're talking about what models can resolve without using a numerical model at all. What we're doing is we're using an analytic solution, a profile for the radial variation of the tangential wind. And we're going to do an exercise on the observations that we have from the Atlantic Basin. And the exercise is as follows, and it's pretty simple-minded. We're going to construct a full radial profile of the wind for each storm in the database, 325 storms, at their time of maximum intensity. And then once we have that profile, we're going to filter that profile spatially with a filter that represents kind of the minimum resolvable scale in a model of a given grid spacing. So that scale, of course, varies with the grid spacing of the model. And if the model is finer in scale, there's barely any filtering at all done to the profile. If the model is coarser scale, you can imagine the profile is filtered a lot. And we're simply going to then look at the distribution of intensity that we get from this exercise. It's done on real data, but it's to think about, what might we expect? And I would say this is kind of a best case scenario in some ways. We're using sort of 2 delta x as kind of the minimum spacing that we would allow. Most models don't really resolve anything at 2 delta x. It's more like 6 delta x where they actually can start resolving features. But anyway, it's an upper bound, we'll say. And so what the next slide is going to be is a sequence of series of climatologies put together. One is going to be the one in black is the climatology from the North Atlantic. So those lines are the number of, it's just a count, the number of hurricanes, the number of tropical cyclones we get in each of these categories. Now, by definition, the black bars, there's nothing in the TD category, that's tropical depression, because everything is at least a tropical storm in this data set. That's, of course, not true as we start filtering. And the point I want to make here is when we filter by, according to what a 1/8 degree model might get, which is 0.125, we don't change the distribution that much. The orange lines are very similar to the black bars, but as we start moving out to 1/4, to 1/2, and to 1 degree, we end up with more and more bunching of the distribution toward the left, meaning we would not expect those models to be resolving many of the more intense storms. And in fact, once we get to 1 degree, we're not even getting any hurricanes. We get like a few in that little blue bar. So, and in this middle category, we get about 1/4 of a degree. We get about half of the major hurricanes and about 3/8 of the intense hurricanes, category 4 and 5. So it's a number to keep in your mind. So this is sort of saying, by this measure, we ought to expect 1/4 degree models to simulate some intense hurricanes, but by far not the number that there are. So that's just kind of what I said. There are different ways to do this filtering. It was a little bit arbitrary. So in this GRL paper, there are also other ways to think about it. We could be filtering angular momentum instead of velocity. We could create axisymmetric wind profiles because the theory we're using technically applies to an axisymmetric situation. And we get about the same number. This plot shows you the fraction of major hurricanes that we get as I'm sorry, yes, the fraction of the observed major hurricanes that we get, no, the fraction of the observed storms that we get in each category, I'm sorry. So in other words, from these different methods. So the method you saw on the previous slide is in blue, and so that result is the same result as we had for a 1/4 degree. The other methods give you broadly similar numbers. And so the line, the horizontal dashed line is at 1. That would mean we get the same number as observed. And so you can see on the right, it's another way of saying the same thing, that we're getting numbers and down to 20% or so on average, or 30% possibly when we get out to categories 4 and 5. And it doesn't really matter how you do this in the details. It's just another way of saying that everything's okay roughly up to about category 3, but not beyond. And of course, those high intensity events are the ones that we most care about. So it's a bit of a cautionary tale. I want to turn attention now, though, to a particular case, and maybe we can see, well, what information can we perhaps get from models that are under-resolved? So this is going to be a little bit of a similar calculation, and I'm going to do it for Hurricane Irma. Some of you may remember Hurricane Irma now. It's almost 6 years ago. This was a Category 5 Atlantic hurricane, formed kind of a classic Cape Verde storm, tracked to the western Atlantic, made its initial landfall, I believe, over the island of Barbuda. Very small island in the, you can see at the bottom of the plot, that's very close to the time of maximum intensity. That's when that picture, satellite image in the right-hand side of the plot is taken. That's a Category 5 storm, and Barbuda is the little island, if you can see it right in the middle there. So not a good day on that island. There was a tremendous amount of damage. So that's Irma, and we're going to be focusing more on that time of maximum intensity. This next plot I want to explain a little bit, because this is a time series that you probably don't see very often, and this is a time series of the radius of maximum wind. And there are different ways to think about the radius of maximum wind, different observations that you can use. So it goes from right to left are the days in September, and the green line is what's called the best track data. Best track is what is distributed widely as, I guess, indicative of the ground truth. It isn't always, and in fact, in terms of radius of maximum wind, it's often highly uncertain. So there are no error bars on here. It's kind of difficult to quantify what those error bars are, but there's some significant uncertainty about that, because it's a hard thing to measure. If you're not flying an airplane in, and even if you are flying an airplane in, you're not down in the boundary layer. You're up at 3 kilometers or so. So it's kind of challenging. Anyway, that's the green line, and you can see that for the most part, especially during the 6th and 7th, which is the time periods over here, that's the time of lifetime maximum intensity. It's relatively constant, at least in the best track. These blue dots are what we call vortex data messages, and they come from the aircraft. Every time the aircraft penetrates the storm, you should get one of these messages that tells you, it'll say in words where it measured the maximum wind, at what radius from the center, because they do a center fix every time they go through. And that's what these dots are. And they often, they're not exactly a great estimate, because they can be fairly asymmetric. So you can get, on one flight leg, you can get one answer, on another flight leg, a different answer. But if you look kind of at the bottom of that distribution, that's sort of where we expect to be, a decent estimate. And then the red line is what is computed from this analytic profile. And you can see it's sort of like the green line, but it's a bit less. And we're going to use that red line here because, A, it does agree reasonably well with the vortex data messages until the storm gets to be interacting with land, and that's Cuba and that's Florida over there on the right. So that red profile, that's what we're going to be using. And we're going to look at forecasts from the, at the time, the global forecast system. This was now 2017, so a few years ago, where the model was run, and I'm not going to remember this, the grid spacing here, it's probably 20-something kilometers. So not as fine as it is now. And the dots on here, these are all forecasts during the time here from the 3rd up to landfall, final landfall on the 11th of September. So every dot is one forecast. The forecasts are not only at the time of maximum intensity, they're for all times. And you can see that there's some spread in the orange dots. So that's the maximum velocity, tangential wind, or the maximum wind at 10 meters in the model. The plot, the other set of the yellow dots represents the radius of maximum wind in Irma. So I just told you that the radius of maximum wind is sitting down around 10 nautical miles, 16 kilometers. And this model is forecasting the maximum wind to be around, let's say 25 to 30 nautical miles. So quite a bit bigger than the real storm. Now, using this analytic profile, we can actually solve for what the intensity would be if the storm followed that profile inward to the observed radius of maximum wind. So in other words, it's a hypothetical calculation saying if that storm could contract further, what would it have produced? And we're going to use this relation here, and that's the same relation basically I showed you previously. We're just substituting. We're basically on this analytic curve, given where the model produces its outer, its maximum wind at a too large radius, and we're going to say what happens if we follow that in to the observed radius of maximum wind, and we get those dots, and those indicate that even though it initially looked like the forecast was good way over there on the right, it actually turns out that there was some information in this forecast about the maximum intensity of Irma, even though the model couldn't explicitly resolve it. And I think what this is saying is that the outer wind structure in this case was pretty good. The outer wind structure is a mess, then if you extrapolate anything in, you're not going to get a good result. So it's saying that, at least in this case, you could potentially derive some useful information if you know something about what the real radius of maximum wind is. Of course, in practice, that may be as hard to forecast as the maximum wind itself. So this is really a diagnostic, not a prognostic tool. But it gets us thinking that, there may be a way to kind of remap what these models are doing at coarse resolution and gain some information at high resolution. So this is, from part one, some simple results here that what I'm saying here is these intense storms, they should be substantially underrepresented for mesh spacings of about 1/4 degree or coarser, according to this kind of simple-minded calculation. And I realize that it is simple, and we would need to do a lot more to say something more definitive. I will say, though, it is kind of an upper bound, what we would expect. And it may be possible to statistically improve intensity in models that are under-resolved hurricanes if we know some other information. Now, this has not been proven. This is a conjecture. The question I want to ask is, if a model is coarse resolution, does not resolve the inner core, and still has the right intensity, is it wrong? And if that is the case, then what are the consequences of it being wrong? And one consequence you could think of is that the storm is probably too big. And if it's too big, it has those winds at too large a radius. And if you think of the area that involves, area goes as the square of the radius. And so things like the total energy extracted from the ocean is going to be too big. Things like this. So there are definitely going to be consequences. I don't think we know in general what those consequences would be, like on the larger scale circulation. But it's something to keep in mind. And it's interpretation about what is your desired result, right? Is it at all costs you need to get the maximum wind even if you can't resolve it, or is it you care about the entire storm and what it's doing in its environment? So I think it's something to think about. Anyway, as a result from this. Okay, that's part one. Leading into part two. And this is where I'm going to talk about the resolution dependence of intensity. I borrowed this figure from a recent paper that came out from Liang et al. In Climate Dynamics, which showed results from the model for prediction across scales, MPAS, which I'm going to be talking about in the rest of this presentation. And this is where they ran for the Western Pacific. They were doing runs over this time period, 26 years, I guess. looking at the intensity distribution of storms they get. Now, they have two configurations of the model. Whoops, the label is a little misaligned there. The blue is a very coarse 1 degree-like resolution, 120 kilometer mesh spacing. The red is a 30 kilometer variable resolution spacing with the 30 kilometers over the Pacific. And what you see is these numbers at the bottom, so tropical storm, category 1, 2, 3, and then 4 to 5. And a little bit like what we were saying in the previous result, when you have a 1 degree model, it's very hard to get anything beyond a category 1 hurricane. Well, that's true here. We get some category 1 hurricanes and a lot of weak storms, just not able to resolve the hurricane. When we go to 30 kilometers now, we're getting stuff way out to category 5, category 4 and 5. So that's an interesting question is, okay, we are able to get some intense storms in this situation. The question I'm going to ask is, oh, there's a question here before I ask my question.
Ready for that question?
Okay.
Is this a long free run, or are these cold start forecasts of some, like from?
That's a good question. I'd have to go back and look.
Okay.
I think they're effectively free in the sense of, I think they're long integrations. They're not a set of like short forecasts. But I should check. The question I'm going to ask is, you know, even though these results for different resolution are very different, are they in some way consistent? Can we say anything quantitative about that? Yes, qualitatively, they're what we expect. So that's going to be what I'm going to talk about in the rest of this talk, and I'm going to use a framework that is, I think, very helpful that Rosemar developed for MPAS, which is the aquaplanet version. So this is a planet very much like Earth, but it's not Earth. It rotates the same way. It has the same sun, has the same ozone in the stratosphere, roughly, in a climatological sense, and it has a prescribed sea surface temperature. And other than that, it's all water. And in this case, the ocean is not interactive. So we're just doing an atmosphere-only kind of experiment. What you see on the right is the sea surface temperature distribution. And you'll notice that the peak at around 29 degrees C is off the equator. It's just a little bit north of the equator. Rosemar, I think, and Brian Medeiros wrote a paper looking at tropical waves in this configuration when you put the maximum at the equator. It turns out when you do that, and you have a maximum of, say, 27 or 28, they didn't get any tropical cyclones at all. And there was a number of reasons for that. But to get a robust sample of tropical cyclones, we put it off the equator. And we're going to look at simulations 3 to 120 kilometer in mesh spacing. I'm saying mesh, not grid, because it's not strictly uniform, but it's very close in MPAS. This is results that were submitted to James recently. So why an aquaplanet? Well, it misses some of the complexity of the real atmosphere. It's not a simple model by any means, but it's more idealized. It won't have stationary waves, for instance, at least none that I could see. You have these quasi-permanent favorable conditions for tropical cyclones, so you get more TCs per day of integration, so it's kind of efficient. And some of the multi-scale variability is simplified. So in looking at things like tropical waves and tropical cyclone interaction, which Rosemar is going to do, it's working on right now, it narrows the parameter space a little bit and the kinds of modes that you have to deal with. So it's interesting. So what does it look like? Well, that's what it looks like. So this is a satellite image, infrared equivalent of OLR, looking at just an evolution. You can see time ticking away on the top. Now this is from a variable resolution, so the 3 kilometer cell spacing is concentrated in the northern hemisphere tropics, north of the equator up to about 30, and it transitions to 12 kilometers elsewhere. You can see the model set up, and these things on the right are the same for every single simulation that we're doing. Of course, they don't all behave quite the same way, and especially the Tietke scheme that Wei Wang developed is used here, and it's scale aware, which means that it's the same scheme, but it tends to turn off the parameterized convection as you get down into the single digits of kilometers. It doesn't necessarily turn it off entirely. So you can get shallow convection still represented. Let's see. By now, you've probably noticed there are plenty of tropical cyclones wandering around north of the equator. Some of these are pretty intense and have long lifetimes. They undergo extratropical transition, et cetera. There's a pretty well-defined quasi-permanent ITCZ in the tropics. And yeah, it's kind of fun to watch this over a while. So what I'm going to do is, in this simulation and the other simulations, is a number of statistics. First of all, we need a tracker to track tropical cyclones, and that's the Hodges tracker with the smooth vorticity field. And then there's a definition of what is a tropical cyclone. So that needs a closed sea level pressure contour and continuously falling pressure for 24 hours. We're not using a wind speed condition, which is handy because then you don't have to have different conditions for different resolution. The 3 kilometer simulation is run for 4 months. The others are run for 3 years. It's a lot cheaper to run the other one, so there's a longer time period. And I'll say a little bit more about that, I hope, near the end. And again, we're considering only the lifetime of maximum intensity for the tropical cyclones in this model, in these periods. So, and also restricting to where the maximum intensity occurs near the tropics, south of 30. That covers most of them, but it makes it handy because then we don't have to deal with some storms in the extratropics that may be of very different origin. Just to show you that, yeah, these look like tropical cyclones. So these are 20 cyclones from the 3 kilometer simulation. These are OLR images. This is actually figure 6 from Rosemar's paper. And you can see, as typically you'd expect, sort of all shapes and sizes of animals in this zoo. Some of the eyes are fairly big, and some of them are fairly small. Some of the storms are rather asymmetric. Some of them are more annular type storms that are extremely symmetric. So get all kinds. And that, I'm not saying that this agrees with the atmosphere. It's just like the model is producing what seems to be reasonable variability in terms of intercore sizes. And I think that's kind of important. So if we look at the intensity distribution for 2 of these simulations, one is 3 kilometers and the other is 30 kilometers, we get very different intensity distributions. So on the left, we have the number of tropical cyclones in Category 1 hurricanes, Cat 2 and 3, Cat 4 and 5, and you'll see these groupings again as I go through this talk. You can see that the 3 kilometer produces a sizable number of intense hurricanes, Category 4 and 5. The 30 kilometer produces none. It barely gets anything to Cat 2. So this is a pretty different result than we saw earlier, where quarter-degree models were getting a lot of Cat 4 and 5 storms. That's interesting. But remember, this is a different planet. It's not Earth. Looks a lot like Earth, but it's not quite Earth. So we can't draw a direct parallel, but it's interesting. On the right is the distribution of radius of maximum wind. So I showed you the observations before, and we'll come back to that later. But this shows that the 3 kilometer has a distribution where the mode is 15 to 30 kilometers. Note the grid spacing the mesh spacing is 3 kilometers, so those storms are very well resolved. There might be 1 or 2 that are marginal. Whereas the 30 kilometer, most of the radii of maximum wind are in this 30 to 60 kilometer range. That's less than 2 delta X. They are not going to be well resolved. And so there's an issue about, well, okay, what can we say then about what maybe those storms could have been able to produce? Like, are they consistent in other aspects? And that's going to be what we're talking about here. Just so you can get numbers on the bottom, it gives you some of the numbers that go into this. But of course, the 30 kilometers is a much longer integration. It actually produces slightly fewer storms per day. I think that should say 3 years and not 2. Anyway, now the next slide is, I kind of apologize here because this is a lot of data to look at, and I wasn't clever enough to figure out a better way to display it. So what you've got here are plots like you saw before for the observations, and this is looking at radius of maximum wind on the y-axis, maximum wind on the x-axis. And I've got 30 kilometers simulation, 60 kilometers, 30 kilometers, 15 kilometers, and over there on the right is the 3-kilometer simulation. So everything on the left, convection, I would say, is mainly parameterized. That's what they have in common. Of course, the physical parameterizations are the same in all these, but they don't work quite the same, of course. On the right, convection is mainly explicit in the model. What you see, a few things here, all of these distributions have a sort of similar shape in that at low intensity, you can get about anything you want for a radius of maximum wind. You get big storms, little storms. It doesn't really, they don't settle down. Remember, the observations did settle down. And on the right side of the diagram, they do all seem to be trying to settle down to some range of radius of maximum wind with intensity. You don't get any major hurricanes with parameterized convection in this model. On those three on the left, nothing is greater than category 3, nothing's greater than 50 meters per second. But you do on the right, and you saw most of those on a previous slide. So there are definitely some differences in these distributions. Again, the question I'm going to ask is can we define whether these distributions are really what we expect in a consistency sort of diagnostic? I labeled on here the 3 delta X line. We're going to be using that. In other words, that's just where the line is drawn at 3 times the grid spacing for the radius of maximum wind. So you can kind of see that except for 15 kilometers is on the margin of resolving things, but the other coarser simulations are not. I'm not talking about 120 kilometers right now. I haven't finished that analysis. So we're just going to stick to these simulations. And what are we going to do? A little bit like what we did before. So we have our analytical profile. Again, this comes from Emmanuel Rotuno and Chavez 2015, which expresses the wind as a function of radius. And I think I didn't mention this before, m sub m is the angular momentum. Think of that as just radius times velocity. We're in the inner core. There's another term, but in the inner core, it's mostly that. That's the angular momentum. And r sub m is the radius of maximum wind. What we can do is, first of all, we're going to ignore the second term on the right there, minus 1/2 FR in the inner core. That means like within 100 kilometers of the center. That term isn't really that important. And we are going to consider points on a curve that intersects the coarse simulation, maximum wind speed, and radius of maximum wind. So we're going to plug those values in for V and R, and we're going to solve this for a new maximum velocity, Vm sub f, so Vm star sub f. So that's going to be the velocity of the remapped storm. And I should thank George for the title remapping, because it's not downscaling, and it's not a lot of other things. So remapping seems like as good a term as any. So that expression, and it's color-coded based on the information going into it. You see it's a function of the coarse resolution radius of maximum wind and maximum wind speed, the fine resolution radius of maximum wind. So we need to know the radius of maximum wind from the high resolution simulation. And we're going to use that information to solve for the hypothetical maximum wind speed. So this is a similar exercise that we went through before. And in what follows, every time you see blue, it's for fine resolution. Every time you see orange, it's for coarse resolution. So we're going to solve for those. And the next slide gives you a little bit more detail on how we do this. So let's say we have a wind profile from the coarse resolution where V sub MC is the maximum wind speed in the coarse resolution simulation. R sub MC is in the fine resolution, is that radius at which it occurs. R sub MF is the fine resolution radius of maximum wind. And so we're going to construct that hypothetical profile and solve for that V star value. So again, pretty simple. And we're going to see how that compares, V star compares with the original and with the 3-kilometer distribution of maximum wind, which we know. So it's a consistency exercise. Okay, there's of course a little bit of a challenge here is that we don't have any way to know how a storm in one simulation relates to a storm in another simulation. They're totally different climates, different simulations. So we have to take a completely stochastic approach. And the storm in the coarse simulation is remapped to every storm in the high resolution. So you end up, if you have M storms at coarse resolution and N storms at high resolution, you get an M by N ensemble of storms. And we're going to look at relative frequency distributions from that ensemble. Now, you can think about this calculation as, I'm going to say everything less than 3 delta x, I'm going to remap. Everything greater than 3 delta x, I'm going to leave alone because I figure the coarse resolution model is probably resolving that pretty well. This 2 delta x really only refers to 2 delta x down here at the bottom in the high resolution, just to show you that, yes, in fact, everything at high resolution is well resolved. That's why we can do this in the first place. So anyway, so this is going to be, we're going to get an ensemble. You match each of these orange dots with a blue dot, and you get this M by N ensemble, and we're going to look at relative frequency. So let me step through this diagram. I'm getting near the end, so I think the timing should work out okay. So on the left side, I've done 2 calculations with the 60-kilometer simulation. Again, blue is the 3-kilometer result, and so you see relative frequency of tropical cyclone and weaker, strong tropical cyclone in category 1, category 2 and 3, and category 4 and 5. The orange is the 60-kilometer original. So in the upper right, you can see that 60 kilometers does not produce any category 2 and category 3. That's what we expect. It really barely produces any category 1, so everything is over here. Now, the remap distribution is in gray. And the remap distribution looks a lot more like the 3-kilometer distribution than the original coarse resolution. So what it's saying is, in this sense, these distributions are reasonably consistent. In other words, even though the 60-kilometer simulation produced nothing that's very strong, it had information in some sense about what, it was consistent with what we would expect a 60-kilometer storm to produce in relation to the high-resolution simulation that we've got. So they look a lot more similar as after this remapping. Of course, this is a simple diagnostic exercise. It's not saying that if we took storms at 60 kilometers and we somehow downscaled that we'd get that result. There's a question behind you, Morris.
Sorry, James. Yeah, why is the 3-kilometer distribution changing in these plots?
Because
Thanks.
It's where I draw that horizontal line in this distribution. And so I can, for 30 kilometers, it's going to be here, okay? For 60 kilometers, it's going to be 3 delta x is going to be up there. And for 15 kilometers, 3 delta x is going to be here. So the blue dots, I'm only looking at remapping everything below that line. So there's a slight difference in the blue dots. And it's mostly just this stuff over here that's weak and kind of amorphous, but that's where those differences come from. Thanks for the question. You can see over here on the right that we have 30 kilometers, and 30 kilometers, it turns out that the high-end intensity is pretty consistent, even though, like we said before, there were not very many, there were almost no intense storms in that distribution. And finally, 15 kilometers, we see that yeah, we still get some, although in this case, we get somewhat fewer than we would have expected. 60 kilometers, you could argue that we get somewhat more than we would have expected. I'll come back to that point, but one thing that we can do is, well, let's compare 60 kilometers and 15 kilometers. And so we're doing that in this slide, and these are very similar distributions once you remap to 60 kilometers. You get almost the same number of weak tropical storms, strong tropical storms, Cat 1, and here, except you get slightly more from the remapped 60 kilometers. So what does this mean? First of all, I would say it suggests that the 60 and 15 kilometer intensity distributions in this consistency definition are more consistent than perhaps either is with the 3 kilometer. That's not at all surprising. We see that a lot when you go to a convective permitting regime. 60 kilometer when remapped does show some stronger storms. It doesn't mean the original had strong storms. It just means that they were stronger than we would have expected. It also seems like maybe we're not gaining a heck of a lot at 15 kilometers because it costs 64 times to integrate, although I think some would debate that point. But at least we can say that these simulations are relatively consistent. So one thing that I haven't shown you is the climates of these simulations, and they're not all the same. So the 60 kilometer and 15 kilometer climates, so in the top, I have zonal mean wind. And remember, this is aquaplanet, so zonal mean wind is kind of the relevant, I mean, there are no stationary waves really, so this is kind of defining the state, climate state, and zonal mean moist static energy. And those two plots on the left, it is really hard to tell the difference between them. Those climates are almost the same. And down here you have the bottom, you have the Hadley circulation, basically represented by stream functions and horizontal mean meridional velocities. They're almost identical. But you go over there on the 3 kilometer result on the right, and you get stronger westerlies in the subtropics, or as you're exiting the tropics. And the vertical shear in that plot in the upper right is getting pretty strong. If you can't see the magnitude there, it's about 14 meter per second jet at 200 millibars and a 7 meter per second easterly flow down at low levels. So that's 20 meters per second of shear. I'm a person who does shear in meters per second. So some do it in inverse seconds, but so tropical cyclone community, you tend to do it in meters per second. That's a lot of shear. And so all these storms are forming in the tropics and they're running into this shear, or a lot of them are, in 3 kilometers. Now, of course, the actual shear a storm experiences isn't that. It's probably something less. But it suggests that because these states are not the same, we might expect somewhat fewer intense storms in the 3 kilometer simulation. And so it might mean that what the 60 kilometer simulation is doing isn't all that unrealistic, even though it has this slightly different state. Moreover, it introduces kind of some of the challenges that we have of comparing storms in different states because of this underlying difference in the background that each storm is sensing. So it introduces a complexity in the interpretation here. Okay, I'm going to start finishing up now with some findings and interpretation of these. So I would say, broadly speaking, when we remap these course resolution simulations that produce nothing like intense hurricanes, we got decently consistent results with respect to the high resolution control simulation where we know the answer. So this is all in model space, right? This is all kind of a theoretical exercise. Doesn't mean we can translate it to the real world, but at least is saying in this kind of framework, yes, there appears to be some consistency, and at least we have a definition of what that should be. I would argue that the most intense storms at 15 kilometers are a little bit too weak. I neglected to point out something. I'm just going to go back here for a second, because I think this is an interesting point when you look at the distribution, and it's going to be a little bit tricky to see. Down here, I said that the distributions kind of flatten out, and once you get to higher intensity, the range of radius of maximum wind is not that as variable as it is at low intensity. But there's this odd behavior here that the actual size of the inner core of these storms tends to increase as the intensity goes up, which is odd. I don't know why. But I think that may factor into this result that 15 kilometers, again, compared with, say, 60 kilometers, seems a bit weak. So that's that. Maybe the 60 kilometer simulation is overdoing intensity a bit, but we note that there are different states between the 60 and 3 kilometers, and so it may be hard to do this direct comparison. 60 and 15 are similar except for the most intense storms. I will say the sample size at 3 kilometers is useful, but it's probably a bit limiting. So running that for a few more months would probably be helpful because this is an underlying distribution that's really important. And again, I'm just addressing consistency here. No causality is implied, and it's also not clear how you actually translate this to the real atmosphere, but I'll say something about that. A couple of questions, there may be other questions in my mind. Does this mean you could actually infer the number of major hurricanes given only course resolution simulations? I would say yes, if you know something about the underlying distribution of radius of maximum wind. But I don't know if we do. So, I mean, we have data from the real atmosphere, so you could try it, you could do it, you could get an answer. I haven't done that yet. And I don't know how to justify it necessarily, but in principle, you could. I think the more important question is, does this mean we could identify trends or sensitivity of hurricane intensity from the course resolution simulations? And for that, we have to know something about the trends or the sensitivity of the radius of maximum wind, the inner core structure of the hurricane. And we definitely don't know about this. How is the inner core likely to change in a warmer climate, higher SSTs? It probably will, but we don't really know that. Although I think there are ways we may be able to say something about that, possibly through the use of very high resolution idealized simulations. We could at least get an inkling for that. And then the plot on the right, I just wanted to point out that there are papers out there that are trying to do basically what the first question implies, which is infer intensity distributions from very coarse resolution simulations. So it's something that people are thinking about. And the last slide I want to come to is back to this radius of maximum wind distribution. And a result that I am puzzled by, I don't quite know how to explain, I've compared the 3-kilometer distribution of RMW and the observed Atlantic distribution of RMW. Okay, so different planets, right? 3-kilometer aquaplanet, doesn't know anything about the real atmosphere, except the broad parameters. And here's the observed distribution in one basin in the Atlantic. And yeah, they're not the same. They're closer than I would have guessed. So why is that? What is that? Does that mean there's something that is maybe more universal about this distribution of inner core size of the tropical cyclone? If that's true, that could be a very useful piece of information. However, as with any anything like that, any promising thing like that, there's maybe a contrary perspective, and not that this is a contrary perspective per se, but Shavas and Naff wrote a very nice paper in 2022 where they related in a parametric sense the radius of maximum wind to kind of 3 primary parameters: Coriolis parameter, the radius of gale force winds, and the maximum wind speed. So around in a circle we go. So they're not independent. But anyway, it's interesting to think about what this means in terms of our ability to maybe infer some information from course simulations. I don't know. I think the case is still open, and that's where I will end. Thank you very much.
We have plenty of time for questions, but I'm going to take the first one, since I had the pleasure of introducing you. And you may have covered this.
And you have the mic as well.
Right, exactly. You may have covered this, I might have missed it. But in comparing coarse resolution versus the fine resolution, is there an issue where sometimes perhaps the coarse resolution doesn't develop a hurricane at all in an environment that the fine does?
They're not matching.
Right.
They're not matching, so it's not, so I think there probably are. In a sense, the distribution of the numbers of cases, like per day, you do get a slightly greater number at high resolution than at coarse resolution. So that suggests that the coarse resolution isn't capturing all the instances statistically that would be captured at high resolution. And as you go to coarser and coarser, like all the way to 100 to 1 degree, it's more the case. So there is that trend. Yeah, that's in there. So but I guess, I don't know if that's a bad thing.
Well, it seems like it would just maybe modify the ability to go from 120 and infer, what would have happened at 3 if at 120 you didn't have.
Right, so you could imagine
events.
that there are
Right.
cases at a higher resolution that would have been hurricanes that are completely ignored.
Right.
Didn't have the resolution, and
Yeah.
so you're not going to have those, exactly. So, but I'm not talking about genesis in this talk anyway. I'm really just saying stuff that gets to its maximum intensity, what does that look like?
Questions? George, I think, was first.
Hi, Chris. How sensitive is that remapping technique to the ratio of CK over CD, the surface exchange?
Well,
coefficients?
in the original paper that Dan Chavas wrote, it didn't look very sensitive. I think if you use CK over CD that's less than 1, you get a slightly broader outer wind distribution, if I remember correctly. The curves weren't that different. So I think there's a little bit there. And so it would point you in the direction where things aren't quite as, it would buy you a little bit in terms of what a coarser model could resolve, I think, a little bit.
It's one of the reasons I ask is I think in MPAS, the models we develop here at NCAR, that ratio is closer to 1/2.
I think it is.
FYI.
Right.
No,
Interesting presentation, Chris. I guess my question is why you're so careful about treading the line between aquaplanet and real world, because tropical cyclones are really creatures of the tropical ocean. So for all intents and purposes, they kind of live on an aquaplanet, not counting landfall and decay. So I'm not surprised that the correspondence between aquaplanet and reality is so good, because tropical cyclones live over the tropical oceans, and we just have more of it in the aquaplanet.
Yeah, it could be. But there are environmental differences between the two simulations that may, make it a little less clear how to relate the two. It would be nice if it's kind of universal and TCs are TCs. I mean, that would be great. I'm a little hesitant to say that right here.
okay, some online questions from Mike Vulik. Sorry if I missed it, but did the different simulations have the same vertical levels?
They did, and it was 70.
Okay. James Pinto, can you say something about the tropical cyclone formation mechanisms in the aquaplanet simulations? Was there any relationship between formation locations and SST gradients?
So I would, leave the mechanisms to Rosimar, because that's what she's working on now, about how things like Kelvin waves and easterly waves in these simulations interact, because those are the dominant wave types. I would say if I had to pick an analogy for where on Earth the similarity might be greatest, it's probably in the Pacific, not the Atlantic. There's no Africa, so there's no African easterly waves. There are easterly waves, but they look rather different. So, and then far as the gradient, so there is no zonal gradient of SST by definition, so it's only the latitudinal gradient. And for the most part, we're looking at a lot of formation where the gradients are quite weak. So I would say I would be hard pressed, except for the formation being south of most of the gradient. I'm not sure that there's a clear relationship otherwise.
Any other questions?
Would you recommend using the tracker that you used for MPAS as opposed to the GFDL tracker?
Probably a question for Rosimar. It seems to be a little less, I'm going to say here, a little less sensitive maybe. It's operating on fairly coarse fields, and so of vorticity, and so it's a little less sensitive to some details. I think GFDL tracker, if I remember correctly, I know you're experienced with it.
Yeah, it required you to remap it to a lat long grid that was quarter degree resolution.
I think the tracker here runs on a Gaussian grid, so it still requires a remapping. I should say, though, that in all this stuff, we go back to the native mesh to get all the statistics once you know what system it is that you're following. So in that sense, I don't think it matters tremendously. It's just what it would matter in is what systems are you picking up, especially in their early weak stages. But for this, I'm looking at maximum intensity, so then it's obvious what you have. So it's not going to affect the results for this study.
Any more questions? If not, unless Chris goes running away. Oh, there is, okay.
Oh,
Just make sure it's not illegitimate. Okay, go ahead.
Andrew Feder, did you explore differences in minimum central pressures among the resolutions? Would these follow similar trends?
Yeah, I did. I didn't have a chance to show it today, but we did look at pressure-wind relationships. And I would say there are similar trends, but one of the challenges you have is that the pressures in all these coarse resolution simulations tend to be a little too deep, a little bit too low given the wind speed. It's just sort of something that happens in coarse models, and I think it's because pressure is an integral. And so you can get a deeper pressure without resolving the eye wall very well. And you see that. So the trends are similar, and you can do the remapping in terms of pressure or wind. You get similar, I'd say broadly similar results, but interpretation is a little bit harder because of this challenge. The pressure field is different over a wide range of radii in the coarse resolution, not just in the inner core. So that's all I could say there.
Well, let's thank Chris once again, and again, he'll be outside, hopefully. for further discussion.